Hi, grade 11 to 12. Welcome back once again to this session. We are still continuing with Euclidean geometry. It's our revision, and in this session, we'll be focusing on our last theorem, which is theorem number 9. So, theorem number 9 states that the angle between a tangent to a circle, right, and a chord, right, is equal to the angle subtended by the two other chords. Okay, and we call this what? Tan-chord theorem, right? What does it imply? Okay, let's look at our tangent. If we are given that ABC is our tangent, then we know that BD is the chord, right? So the angle between the tangent and the chord, maybe let me use a different color. So the angle between the tangent and the chord, this is the angle, right? Can you see? This is the angle here, angle B, it's angle DBC, right? The angle between the tangent and the chord is equal to the angle subtended by the two other chords on the circumference. Very, very important. And this is what really the theorem states. Hence, we call it a what? A tan and a chord theorem. In other words, when you give your reason, you just say tan-chord. Okay, so obviously someone can argue to say, oh, we still have another angle between a tangent and a chord. This is still a tangent and this is still a chord. Here is the angle we have, right? So this angle between a tangent and a chord, it will be equal to the angle subtended by the two other chords on the what? On the circumference. On the circumference. Meaning that we can also deduce that angle EBA will be equals to what? Will be equals to angle D, but rather it's not really an angle D, but it's angle EDB, right? Is this angle there? Angle EDB, and here it's not really angle E, but rather it's angle BE what? BED. Okay, so that's what theorem 9 states, right? But on a given statement, they're saying the angle between the tangent to a circle and a chord drawn from a point of contact is equal to the angle in the alternate segment, right? So in the other segment, or rather the angle subtended by the two other what? By the two other chords. Okay, let's now take a look at the proof of this theorem. And this is one of the most examinable theorem that you can find, right? Examiners know it's quite a little bit tricky. They will give you and they will say prove this theorem. They will give you 7 marks or so. So by you just learning how to prove it, you know that you have your 7 marks that is guaranteed, right? In case they bring it. Okay, so they want you, they gave you that ABC is a tangent, right? And they also said you are required to prove that angle CBD, this angle here, is equal to angle BED, this angle here, right? Angle between a tangent and a chord is equal to the angle subtended by the two other chords on the circumference. They want you to prove that. Okay, so we're just gonna start with construction. Very, very important. How do we construct? What you do is you construct a diameter first, right? Meaning I'm gonna construct a diameter. I'm joining point from B, passing through O, going to F, to a certain point on the circumference, right? So we'll just tell them join line from B to F, right? Passing through O, obviously. Or we can say join diameter, or rather form a diameter, right? I think that's much better. Form a diameter from B to what? To F. That's what we did. Then very, very important, it's your second construction. And this is where most learners make mistakes, right? Look at the angle that you want to prove, right? You want to prove that this angle B is the same as angle E. So what you do, you come and construct a chord that goes towards the angle you want to prove in the circumference. Let me repeat that. You construct a chord that goes towards the angle you want to prove, towards the point where the angle is, right? That you want to prove, that is on the circumference. Meaning that we're gonna construct a chord from F to what? To E. So don't make that mistake and you come and construct from F to D, because most of learners make that mistake. Because we don't care about D. We don't want to prove it, right? So we want to prove that angle CBD is equal to angle BD. Hence, we construct towards that thing so that we can have a relation between the thing, right? So we can now say join line from what? From F to what? To E. Then we can come and name, this is angle 1, this is angle 2, right? Also here we can just name this is angle 1 and this is angle 2. Okay, so we can now go and prove now. It's much better in this way. We can now go and prove. Remember, we want to prove that angle CBD, in other words angle B1, is the same as angle BED, which is angle what? Angle E2, right? We want to prove that. Okay, so according to this construction, we can see some of the relational approach coming into place here. We have a radius and we have a tangent. We are given that ABC is a tangent. What do we know from theorem number 7? What do we know? Radius is always perpendicular to what? To tangent. In other words, we can deduce that angle B1 plus angle B2, they're equals to what? 90 degrees. Why? Radius perpendicular to what? To tangent. That's always the case, according to theorem number 7. Okay, so what can we see again? This is a diameter, right? What does a diameter do? According to theorem number 3, the angle subtended by a diameter at the circumference is a what? Is a right angle, meaning that our angle E1 plus angle E2, they are also equals to what? 90 degrees. Why? Angle in what? In semicircle, right? Or rather, angle subtended by a diameter. Okay, so can you see now there's some relation here? B1 plus B2 is 90, E1 plus E2 is 90. We can deduce what? That therefore, angle B1 plus angle B2 is the same as angle E1 plus angle what? Plus angle E2. Why are we equating them? Because both of them are equals to what? 90 degrees. Okay, both of them are equals to 90 degrees. Hence, we are equating them. All right. Okay, let's take a look at another theorem. We can see some oxbow sort of like tie there. And we said something about this theorem that sort of like form an oxbow tie where the circumference, where the vertex are on the circumference. What can we deduce about these angles? Very, very important. Angle E1 is actually the same as angle what? As angle B2. Why? Because these are angles subtended by the same arc at the circumference. Same arc at the circumference. In that oxbow tie, remember that theorem? Angles in the same segment are equal, right? Meaning that we can say, but we can see that our angle E1 is the same as angle what? As angle B2. Can you see? Our angle E1 is the same as angle B2. Why? Because these are angles at what? At same segment. Angles at the same segment are equal, or rather angles subtended by the same chord, or rather angles subtended by the same arc, right? Meaning that I can now go and cancel out E1 and B2 because they are equal. We are saying B2 is equals to what? Is equals to E1. So if these two are equal, and when you transpose the other, it's just going to cancel, right? But for you to be able to see this clearly, where there is B2, I can just place E1, right? Because E1 is the same as B2. Then you can see, so can you see now? So this is E1. So E1 and E1 will cancel out each other because when you transpose, when you take E1 to the other side, it's going to be minus. So E1 minus E1, they go away. Therefore, we are left with angle B1 is actually the same as angle what? as angle E2. Can you see? We have proven the theorem. Let me just delete all these things here and just show you what we have just proven now. We've just proven that indeed angle B1, which is this angle, which is the angle between a chord and a tangent, is the same as angle E2. Can you see? Angle subtended by the two other chords on the circumference. And we know that B1 is the same as what? Angle CBD. And angle E2 is the same as what? Angle BED. Meaning they are equal. Okay, so that's actually how you prove this theorem. Okay, let's quickly take a look at some examples. Okay, let's now take a look at these examples. This is diagram number 1 and this is diagram number 2. Okay, they want you to solve for x and y in both these diagrams. We're just going to start with diagram 1. What can we see from diagram 1? We are given that ABT is a tangent, right? So that is the given information. And if ABC is a tangent, what can we see? We see that 40 degrees is an angle between a tangent and a chord, right? What do we know about theorem number 1? Angle between a tangent and a chord is equal to the angle subtended by the two other chords, but on the what? On the circumference. This is very, very important. So meaning that our 40 degrees is the same as what? Our 40 degrees angle between tangent and this chord BP is the same as angle subtended by the two other chords on the circumference. Meaning that 40 degrees is the same as what? As y by what? By tan-chord. And that's our reason. Okay. So let's go and solve for x. So with x, it's also an angle between a tangent and a chord, right? Here is it. So angle between a tangent and a chord will be equal to the angle subtended by the two other chords on the circumference. Okay, so meaning that our x will be equal to what? 100 degrees by what? By tan-chord theorem. All right. Okay, so that's basically how we solve for x. Okay, so you can get something like this, and I want you to be very aware and not to make this mistake, right? Because a lot of students tend to make it. You can get something like this, and maybe you are given here maybe 100 degrees, maybe x. A lot of students might make a mistake here to say this angle x is equals to 100 degrees, angle subtended by the two other chords. This is wrong. It's not correct. Why? Because we are saying the theorem states that angle between a tangent and a chord is equals to the angle subtended by the two other chords on the circumference. This angle firstly is not on the circumference, right? Number 2, these are not chords, but they are what? They are radius. Can you see? So don't make that mistake to see if you just see a triangle and there's an angle between a chord and the tangent, you just equate it. Check properly whether it's subtended by the two other chords on the what? On the circumference. And for you to check that, you just simply need to check, is my triangle a vertex touching the circumference? All of them, right? So if you find that your triangle vertex are touching the circumference, just like in diagram 1, that triangle had its vertex on the what? On the circumference, then we can now use the tan-chord theorem. Okay, so yeah, just make sure that you don't do that mistake. Let's move to diagram number 2. They also want you to solve for x and y, right? Okay, so how are we gonna solve for x and y here? Very, very important. Let's look at something here. You have an angle between a chord and a what? And a tangent, right? They told you that ABT is a tangent. So we know that the angle between a tangent and a chord is equals to the angle subtended by the two other chords, but on the what? On the circumference, meaning that we can deduce that angle D1 is equals to what? Is equals to 40 degrees. By what? By tan-chord. Can you see? Angle D1 is 40 degrees by what? By tan-chord. Okay, So to solve for y, it's quite simple. It's on that triangle. We can use some angles of a triangle. It's 180. They're supplementary, right? So meaning that we can say y plus what? Plus 40 degrees plus what? 56 degrees is equals to 180 degrees. Why? Some angles of a what? Of a triangle. We know that some angles of a triangle are supplementary. Okay. So to solve for y, we're just going to transpose 40 and 56, right? So y will be 180 minus 40 minus 56, which will give us 84 degrees. Okay, so where there is y, we can put 84 degrees. Okay, let's go and solve for x now. Okay, so before we solve for x, I just want you to take note of the following. Someone might ask, but say, why didn't you say x is 40 degrees? Right, there can be that misconception. Why didn't you say angle between tangent and chord is equals to angle subtended by the two other chords? This is because this angle here, right, is between this chord of this triangle. So we have to be relating it to that triangle only, not the other one, right? For this triangle, obviously, you'll relate which angle? This side, right? Because it's between this triangle there. Hence, we just equated it with D1 and not angle E. Can you see? So take note of that. Okay, let's now go and solve for x. We have our y as 84 degrees, right? How can we solve for x? Let's take a look at BEDC. What can you notice about BEDC? Okay, BEDC is a what? Is a cyclic quadrilateral, right? Which theorem comes to your mind when you think of cyclic quadrilateral? There are two theorems, or rather three theorems that must come to your mind. Angles at the same segment are equal. That's the first theorem that must come to your mind. Number two, opposite angles of a cyclic quad are what? Are supplementary. Number three, exterior angle of a cyclic quad is equals to the opposite interior angle. Which one of the three can we use? Obviously, we can't use the one that say angles angles at the same segment are equal, right? Because we don't have that oxbow there, right? Obviously, we can't use the one that say exterior angle of a cyclic quad because we don't really see an exterior angle here. You can't say this is an exterior angle, right? Otherwise, there must be a straight line going like that. Then we can say this is an exterior angle of a cyclic quad, right? Or rather, this is an exterior angle, but it's not really in the direction in which we know the theorem is all about. Okay, so meaning that to solve for x, we're just going to use what? The one that says opposite angles of a cyclic quad are what? Are supplementary. Meaning that 84 degrees plus x is equals to what? 180 degrees. Why? Opposite angles of what? Of cyclic quad. We know that opposite angles of a cyclic quad, they are what? They are supplementary. Okay. You have to be thinking of this theorem really, and it's quite very easy to do this if we just apply that thing. Okay. So we're just gonna say x is sorry about that, 180 minus 84, which is equals to what? 96 degrees. Let's now look at the converse of theorem number 9. Okay, the converse, like I said, they are very, very important, right? Because this is where you get your examiners asking you to prove certain things out of them, right? And they have a lot of marks, and a lot of learners tend to undermine converse theorem, thinking that, oh, it won't come, let me just know the theorem. No, if you know the theorem, you must know the converse. It's very, very simple, because the converse is just the sort of like a reverse of the theorem. To say, if the theorem states that if this is this, then this will happen, then the converse now, it's starting with then will happen, right? And this is this. So something like that. It changed the statement into a deduction, and a deduction into a statement. So that's a converse theorem. Okay, remember the theorem now states that the angle between the chord and the tangent will be equal to the angle subtended by the two other chords on the circumference. Now the converse is saying, if you find that an angle between the circumference, if you find that there's an angle subtended by the two other chords, right, on your circumference, then being equal to what? Being equal to the angle between the chord and a certain line, then you can now deduce that actually there is a tangent there that actually makes that thing happen. Okay, maybe I'm not clear there. Let me just read for you. It says, if a line is drawn from the end point of a chord, right, making the chord an angle equal to an angle in the alternate segment, right? So they're saying if you have something like B2, there's an angle between an end point of a chord, making that angle being equal to the angle in the other segment. Then the line, this line here, will be what? Will be tangent to a circle. And our reason for that is that angle between a line and chord. We can see that the angle between a line and chord is equal to the angle in the alternate segment. Then we can deduce, oh, actually that line we're talking about is a what? Is a tangent. So the question you can expect here is those questions that says prove that this is a tangent, right? You can use this theorem, the converse of it, to say is there an angle between that line I want to prove whether it's a tangent and a chord? Is that angle equal to the other angle in the alternate segment, or rather the other angle subtended by the two other chords? If that's the case, we know that that's a converse of theorem 9. Then we can deduce, oh, actually this line is a what? Is a tangent. But that's not the only way we can prove it that is a tangent. We can just check if we have a radius and if it's perpendicular to that line, then we can deduce, oh, this is actually a tangent, because radius is always perpendicular to a line, which is called a what? A tangent. So there are many ways in which you can prove a tangent, but in this lesson we just want to focus on this very, very key exam kind of question. You can expect it in your exam paper because it's quite tricky, but it's very simple. Hopefully you'll understand it after we just do some quick examples. Okay, let's start with this example number 1. They are saying prove that PT is a tangent to the circle if angle P4 is equals to 60 degrees and angle BCP, that is the whole angle here, they've shown you it's 120 degrees when C1 is equals to C2. Okay, and this is a fairly quite easy question. How can we prove that this line PT is a tangent? If we can be able to prove that an angle between this line PT and a chord is actually equal to the angle in the alternate segment, or rather the angle subtended by the two other chords, then we can conclude, oh, this is actually a converse of theorem 9, then meaning that that line is a tangent. Simple as that. Okay, so we can see that P4, so what you are required to prove really here, if you can manage to prove that angle P4 is equals to angle C2, because C2 is the one in the alternate segment, or rather an angle subtended by the two other chords, then you can deduce, oh, it's a converse of theorem 9, then tan-chord theorem, right? Angle between line and chord. Okay, so let's go and prove that. We know that our angle P4 is equals to what? 60 degrees, right? Let's go and calculate C2. We want C2. We are given that C1 plus C2 is what? Is 120 degrees. Very, very key. But C1 is equals to C2. We are given on the statement. Meaning that we can replace C1 by what? By C2. And go and solve for what? For C2. So 2C2 is equals to 120 degrees. Okay. So it's going to be equals to 120 degrees. And we're just going to divide by 2 both sides. Divide by 2. Then our C2 is what? Is 60 degrees. And what does this mean? If C2 is 60 degrees, then it's equals to what? Is equals to P4. Okay. So we can deduce that P4 is actually the same as what? As C2, because both of them are equals to what? 60 degrees. What does this imply? If P4, right, it's a bit of a mess here. If P4 is equals to C2, what does it mean? It means that the angle between a line and the chord is equal to the angle subtended in the other alternate segment, meaning that it's a converse tan-chord theorem, right? Meaning that here it proves that PT is a tangent, because that can only be possible because a tangent and a chord, the angle between will be equal to the angle in the alternate segment. So we can now prove that therefore PT is a what? Is a tangent, because what? The angle between chord and the angle between chord and tangent, or rather the angle between line and what? And chord, or someone can just say converse theorem 4, right? Okay, let's now move to this example, just for your understanding, to enlighten your understanding on this. Just put for you another example there. It says prove that SRT is a tangent to the circle through PQR. In other words, they are saying here there's a circle PQR, right? But it's not there. They just give you this kind of thing. They are saying prove that SRT is a tangent. How can SRT be a tangent? If we can manage to prove that this angle between a tangent and this line will be equal to the angle in the alternate segment, right? If we can manage to prove that, then we can prove, oh, actually it's corresponding to theorem number 9. Then that's how we can prove, similarly to what we did here, right? So meaning we have to first solve for x, right? If we solve for x and we go and replace there, probably we're gonna get 64. Then we can prove, oh, it's actually a tangent. Okay, how can we solve for x? You don't come and say 4x is equals to 64. Very, very wrong. There's no circle here, right? Meaning that, and also you are not allowed to use this as a tangent. You want to prove that this is actually a tangent, right? So you don't use any property that are related to tangent. You have to use other things, and they will obviously provide you other things to use. Just like here, to solve for x, we are provided by a straight line, right? Angles in a straight line, they all add up to what? To 180 degrees. Then we can now go and solve for x, right? That's how we do it. So we just say some angles of a what? Of a straight line. Some angles of a straight line. We know that they are supplementary. So 5x plus x plus 4 is going to be 6x plus 4 is going to be 10x is equals to 180 minus 20 is going to be 160 divided by 10. Our x is going to be what? 16 degrees. Okay, x is 16. We can now go and calculate and put our x there, right? So we are saying Q angle RT is equals to 4x. Where there is x, we're just going to put what? 16. So 4 times 16 is going to give us what? 64 degrees. Meaning that we can deduce, therefore, we can see that Q angle RT is actually the same as angle P, because both of them are equals to what? 64 degrees. Therefore, we can conclude, indeed, SRT is a what? Is a tangent. And why are we saying is a tangent? By converse theorem what? 9. Or rather, you can just say angle between line and what? And chord is equals to the angle in the other segment. Okay. Okay, grade 11 to 12. This marks the end of our session. Thank you very, very much for joining us in this revision session from theorem number 1 up until we reach our last theorem, which was theorem number 9, tan-chord theorem. Otherwise, grade 12, practice makes perfect. In the upcoming sessions, we'll just be looking at some application of all this theorem in one question, looking at past papers and actually showing you how you can actually tackle this topic. topic. I know that most of you might be exhausted now to say, oh, there's a lot of theorems that I need to know, there's a lot of proof. Worry not, just take it easy, one at a time, one at a go, and we're just gonna make this until we reach our final ends. Okay, otherwise that's all from me. Thank you very much for joining, and goodbye.